Okay, guys, welcome. Today we're going to talk about Pythagorean triples. Now, the Pythagorean triples are a nice next step after we study linear Diophantine equations, because now we're studying sort of a nonlinear setting here, but it's something that we're already familiar with, right? So if we look at the Pythagorean theorem and we study the integer solutions, there's a lot of solutions that you're already familiar with at this point. Now we're going to talk about how we can find all of the Pythagorean triples, which is a pretty cool idea. Now, what we have here, don't forget that the Pythagorean theorem is really the equation of a circle with a specific radius, right? So this is a circle centered at the origin of radius z, right? And the idea how this relates to Pythagorean theorem in triangles is that x and y are your height and width of the triangle, and then your radius would form the hypotenuse. So that's how we know that this works. So what we're going to do is we're going to parameterize the circle with a line. And doing that's going to allow us to find all of the triples, right? And one thing that's pretty cool about this is that there are infinitely many distinct triples that we can find for this. And of course, by distinct, we mean that if we know that A, B, and C is a solution to X, Y, Z, then any multiple of that would not be a distinct solution, right? So we mean completely different A, B's, and C's, right? So in other words, 3, 4, 5, and 6, 8, 10 would be considered the same solution because they're just multiples of each other, okay? Now to do this, we're going to divide both sides by z squared. So now if we do that, our equation looks like this. So it's x over z squared plus y over z squared is equal to 1, okay? So now we're looking for rational solutions to the circle in the plane that's u squared plus v squared is equal to 1, or in other words, the unit circle. Right? Now, in order to do this, we're going to first select a rational point of the form 0, comma a over b. And we're going to suppose that we want to connect it to negative 1, comma 0. Now, the equation for this line in point slope form, right, if we know that we have our slope is a over b minus 0 over 0 minus a negative 1, is just going to give us a over b. So that's where your slope is coming from here. Now, if we plug in our coordinate that we want to connect it to, right, if we plug in negative 1, comma 0, then we get the equation is now y is equal to a over b times x plus 1, right, once you drop the 0, of course. Now, just to keep in mind, a few things that are interesting to note here are as follows, right? Now, to find where a line intersects a circle means you're solving a quadratic equation, because a circle is x squared plus y squared equals c squared, and a line is y equals mx plus b. And if you combine these two equations, you're just substituting in here, and now you have a quadratic equation that you would need to solve. Now, another thing to note is that when you solve a quadratic equation, if one solution is rational, then the other one also has to be rational. And you can sort of verify that with the quadratic formula. And another thing is that if a line has rational coefficients and it intersects a circle in 2 points, one point being an intersection that's rational implies that the other is also rational. All right, it's kind of weird English there, but I guess that's all correct. Okay, now therefore, since the line v minus 0 is equal to a over b times u plus 1, here we just replace y with v and x with u. If that intersects the circle at negative 1, comma 0 and has rational coordinates, it's very likely that it's going to intersect the circle again. And in that case, it will also be a rational point. Okay. Now, if u squared plus v squared is equal to 1, and we know that this relationship between u and v, then we can plug this in for v, and we get u squared plus a squared over b squared times u plus 1 squared is equal to 1. Now, if we use the quadratic formula, we'll find that u is equal to negative a squared minus b squared over a squared plus b squared. And v is equal to 2ab over a squared plus b squared. Now we know that u is equal to x over z, and v is equal to y over z. So then we can split x into b squared minus a squared, y into 2ab, and z equal to a squared plus b squared. And these will generate all the Pythagorean triples. And for example, if you choose your a to be 1 and your b to be 2, this gives x equals 3, y equals 4, z equals 5. Okay, so let's do some examples. So we want to find a and b such that x is 5, y is 12, and z is 13. Now, usually when I do this, I like to look at y first because we know that that's 2 times a times b, right? Now, what would be some things that jump out to us that would definitely work? Well, it looks like if a were 3 and b were 2, that should work, right? And if I do x, which I can say is a squared minus b squared, what did I say here? I said it's b squared minus a squared, so I guess I should make a2 and b3. So then I would get 3 squared minus 2 squared, or 9 minus 4, which gives x equals 5. All right, so now we just need to check that z is a squared plus b squared. So we get 3 squared plus 2 squared. So 9 plus 4, so 13. So that is the a and b and c that will do the job. Okay. Now let's look at for b. All right, and I actually have this wrong, right? Because the way that it's listed, I can't get y to be 2ab here, right? So if that's the case, we just switch it and we look at, we were going to pretend that x is 15, y is 8, and z is 17, right? Because when you're solving the Pythagorean theorem, or I should say verifying the Pythagorean theorem, you're never concerned with the placement of x and y as long as the hypotenuse is the hypotenuse. So if we have 2ab, let's try b is equal to, let's see if will it work if they're both 2. Right, and of course the answer is no, because 2 squared minus 2 squared would be 0. All right, so we can't use 2 and 2. So what we could do is maybe do a 4 and a 1. Right, and that would give me y is equal to 8. And then x would give me a 4 squared minus 1 squared, or 16 minus 1, which is 15. All right, then for z, we get a 4 squared plus 1 squared, which gives me z equals 17. All right, and there's the a and b that generate this particular triple. All right, and of course you can find any triple by picking a positive integer for a and b, and that will work, right? And as long as they're different, you won't get trivial solutions. So that's one thing that's pretty cool about this. Okay, so that concludes this video on Pythagorean triples. I hope you enjoyed, and I will see you next time.